Hello, in this video we study inverse functions. Before that, let's remind you about functions. Okay, so suppose that you have a function f from a set A to a set B. What is that? That is a rule that sends all elements in A into B, right? So you might think about, yeah, this is A, this is your B. Each element in A is corresponding to some element in B. So let's say Y, and this is F. So we can write F Y equal to F of X, right? That is about, definition of function. Each element in A is corresponding to some element in B. Okay? If you look at this picture, like you are in the position of X, you apply the transformation F. So you go to the position Y in the B. And suddenly, you want to go back to the position X. Okay? So if you want to go back, you have to answer on two questions. Okay? The first question, is it possible or not? Right? If that is possible, so you need to find a way, right? The way to go back. Is that correct? So that means if that is possible, we need to go back. Okay, you need to find a way to go back from the point Y to the point X. And of course, that can be realized by another function. And we denote by f to negative 1. And we call that is the inverse of f. Okay, if, of course, that can be done for any elements in X. Okay, for any elements in X. So based on this observation, we may define the inverse function of a function. Okay, so if that is possible, don't forget that. Here's the definition. Suppose that you have some function f. Okay, a function g is said to be the inverse of f if the composite f and g at x equal to x for any x in the domain of G, and the composite G with the f at x equal to the x for any x in the domain of f. So basically, it says, yes, you are in the x, right? Suppose you are in the x in the domain of G, okay, in the domain of G. Or let's go back to this picture. Actually, this is your G, right? So G is the inverse of f if you go from x to the G, right? And then you go back. That means you apply another function, right? You apply the G. So that means, G of f of x. You see this? This equal to the x, right? For any x in the domain of f. That means in A. For any x in A. You see this? So for any x in A, you go to the y in here, and then you go back. You go back exactly to that position. Or n, sorry. For if you are in this position, in the y position, right, in the B, you apply g, you go to the x, and then you go back. That means you apply f of g of x, right? And that is exactly x. Again, but this is for any x in the B. So in that case, f and g are called inverse of each other. Okay, so that is the definition of the inverse function. Let's consider the following simple example. You have function f of x equal to x plus 1. Let's find the inverse of this function if it is possible. Okay, so from the definition of this function, we can see that this function sends xx to x plus 1, right? So that is just about addition. If you want to go back to the previous position, you just do subtraction. Is it correct? So, yes, it seems like it is possible, right? And the inverse of this function, f to negative 1x, is equal to x minus 1. Just under the addition means you do subtraction. Is it okay? If you look at the picture right here, so you are in the position x in here, right? Okay. In order to find the y, you just, make a vertical line, and that vertical line will intersect with the graph of y equal to x plus 1 at some point. And that is, you can find the corresponding value of the y right here. Is it correct? Then, if you want to go back to the x from the position of y, right, you need to make some horizontal line, and that intersect with the graph at some point, then you go back to the x. So like you rotate, right, the system of coordinate. That means you need to solve this equation with respect to the x. Is it correct? We need to solve the equation with respect to the x. Right? You write y equal to x plus 1 means, you want to find the y depending on x, right? But now you want to go back. That means, y plays the role of variable and x plays the role of functions, right? Of the y in this case. So that means in order to find the inverse, you need to solve the equation with respect to the x. Okay? So based on this, if you solve this equation with respect to the x, you have the following one. You have x equal to y minus 1. Okay? So, yes, your inverse may look like this. But, that is the when you talk about the function, so you just interchange the variable. So, in this case, I can write actually the inverse of x equal to x minus 1. You see, I just changed the y in here, right? I just replace the y with the x. So I got this. And if you compare this result with this result, they should be the same. You see? So the inverse of addition is subtraction, right? So based on that, you have this formula. But at the same time, if you want to solve this problem analytically, means you want to go from x to the y, that means you express y as a function of x. But if you want to go back from the y to the x, right, you need to express the function, x as a function of y. That means you need to solve the original equation with respect to the x. Okay, so this is how we can explain the picture. Okay, we can solve this in two ways. But usually, such ways, yes, is very, very geometrically, right? Right, so yeah, you say you want to you go to the new position, you undo that, just undo that, right? Just go back. So you add 1, you need to subtract 1. Similarly, you can think about if you have a function y equal to f of x equal to cx, that is multiplication, you want to undo the multiplication. That means you want to find the inverse of this, right? So the easiest way is to divide. Is it correct? So you might think about the inverse of this function is equal to just 1c and x. Okay? But if you want to see this analytically, we need to solve this equation for the x. Okay? So we solve that. I get x equal to 1 over c y. And then from here, I need to interchange. I need to replace y with the x. Okay, so I can write, in this case, the inverse of this function is equal to 1 over c x. So you get exactly the same like this. All right? But again, right, in this example, we need a condition that c is not 0. Okay, we need a condition c is not 0. Why? Of course, you can see, if c is not, if c is 0, you can divide by c, right? But what happens if c is 0? If c is the 0, your function is constant, y equal to 0. What does it mean? That means you send every point, right, x right here, into one position, 0. You see that? But in that situation, when you go back, right, every point to just one point, every point just one point, every point just one point, and you want to go back. You don't know how to decide. You cannot decide. You go from this 0 to this guy, or to this guy, or to this guy. There's no way to make that. Does that make sense? So we need some conditions, for a function can be invertible, okay? Can be invertible. All right, let's consider more complicated examples. We have function f of x equal to 2x cubed minus 1, okay? So let's find the inverse of this function, okay, if it is possible. So let's say, find the inverse if possible. So I will put y equal to 2x cubed minus 1, because I want to look at this function. As you know, you have an x in here, and then you have another point y right here. So I hope you remember the picture on the previous example. I try to solve this equation with respect to the x, okay? I try to solve the equation with respect to the x, okay? So if you solve this, you get 2x cubed equal to y plus 1, and then you divide both sides by 2, you get x cubed equal to y plus 1 over 2, okay? And now you apply cube root. You get x equal to cube root of y plus 1 over 2. It looks good. We could be able to find x, right, as a function of y. So from here, the inverse is f to negative 1 x equal to cube root of x plus 1 over 2. So basically, you need to replace x with the y with the x in here, and you get the inverse function. Okay. So how do you think? Do we need to check? Do we need to check that? If we say that this function is the inverse of the previous one, so we need to check the following condition: f composite with f to negative 1 at x equal to x, and f to negative 1 composite with f at x is also equal to x, right? Of course, this x is in the domain of the inverse, but this x is in the domain of the function f, okay? And we see that the function f and f inverse are defined everywhere, right, on the whole number line. So we can say, we need to check these two conditions for any x in R in the number line. Okay, let's check one of them, okay? So I might choose the first one. So we have f to negative 1x. What's that? So that is f of f to negative 1, so that is cube root of x plus 1 over 2, right? So we need to apply the function f to this value. So let's say, what is f? Our function is this, okay? 2x cubed minus 1. So I write this is equal to 2. X is right here, right? X cubed. So I have cube root of x plus 1 over 2 cube minus 1. You see? So of course, you have cube root and m cube in here. That will be cancelled out, and you get 2x plus 1 over 2 minus 1. And this is x plus 1 minus 1, which is x. Perfect. You are good, right? So, of course, another identity will be will be okay. So, you know, these functions are inverse of each other. Let's say this guy is the inverse of this guy. All right, let's consider. All right, let's change the function a little bit. Now I don't want cube root, I want square root. Let's find the inverse of this function. If possible. Right? So look at this. If we follow the same logic as in the previous example, I need to solve for x, right? Okay, let's do this. I have 2x squared equal to y plus 1. From here, I get x squared equal to y plus 1 over 2. Okay? And when you apply the square root, you get square root of x squared equal to square root of y plus 1 over 2. Okay, in this case, I suppose that y plus 1 is greater than or equal to 0. Okay? But square root of x squared would be absolute of x. Okay? So that is not only x, that should be absolute of x. Don't forget that. Y plus 1 over 2. If you have this equation, x should be equal to plus or minus square root of y plus 1 over 2. You see this? So that means for each y in here, you might have two values of x. Because you have plus minus in here. You see this? So for number y, you have two values of x. That is not a function. You see? This is not a function. So it seems like this function does not have inverse. This function does not have inverse. You see? Because corresponding to two different x in the domain of this function, you have one value y. You see? In here, it says, yeah, corresponding to one value y, you have two values of x, right? Two values of x are corresponding to one value of y. So that is the reason why this function does not have inverse. So if you remember the previous example, when we study y equal to c of x, right? We say if c is 0, there's no way. Yeah, the function does not have inverse. Why? Because, you know, when c is equal to 0, the y is just 0. And that means, you know, you send all x into just one point, right? All different x into one point. You cannot go back. The situation is the same right here. If you apply the function 1x, right, you go to the y, right? You go to the y in here. This is your x. You want to go back. But actually you have two ways to go back. You may go to negative of this value, or you might go to positive of that value. And of course you don't know how to decide. Does that make sense? So based on this observation, we have the following picture. Your function should look like this. Something like this. I suppose, you know, that is the graph of your function, right? And each x is corresponding to one y in here. And each y is corresponding to only one x. Okay, so in that situation, yes, you are good. Your function might have the inverse. Now look at the picture of the parabola. Y equal to 2x squared minus 1. Okay, the picture of this looks like this. This is x, this is y. So you want to find the vertex. Vertex should be x equal to -1, y equal to 0. Let's say right here. This is -1, this is 0. That is the vertex of the parabola. When x equal to 0, the function is -1. Interesting. -1 right here. Let's see. X equal to 0, y equal to -1. So that is the vertex. When x equal to 1 and -1, the function is 0. Okay, it looks good. X equal to 2, the function is equal to 8 minus 1 is 7. Okay, 7 is right here. Suppose that 7 is right here. Okay, so you have the following one. This is the graph of your parabola, right? So, okay, look like this. Look at this. Interesting. Here's -1, okay? So, if you have a function like that, y equal to 2x squared minus 1, and you don't say anything about the domain, right? So, the function is defined everywhere. Let me write it down. Your function f of x is from R to R. So if we don't say anything about the domain, right? So the domain is the whole number line because, the function is defined everywhere. Okay, so for each x right here, yes, you have one y. Okay, that's good. But for each y right here, you see, you might have 2x. You might have x in here and you might have negative x in here. So that's why, in this case, the function does not have inverse. Makes sense? When you consider from R to R. But, again, right, I can consider the restriction of this function. Restriction of the function. What does it mean? That means I want to restrict the domain. I don't want to consider on the whole number line. Because I try to avoid the situation when for each y in here, I have 2x. Look at this. And of course, I didn't talk about, the other, situation. When you pick some y in here, right? You don't have any x. You see? Because this y is also in the R, right? In the number line. But for this value, out of that, which is less than -1, you don't have any corresponding value x. So, which is not good because, you cannot go back, right? So we need to restrict the domain. And not only the domain, we need to restrict, the set right here. The function is from A to B. Don't forget that. Don't forget that. And it really depends on the A and the B. Okay? Now, let's do that. I will restrict the domain, right? I say I don't want this part because I just want to ignore, right? I just consider just a half of the parabola in here. Okay? But that is not all. I need to avoid this interval. So I will consider the function f from R plus, or let's say from 0 infinity, right, to -1 infinity. You see this? So what does it mean? It means and I send x2 to y equal to 2x squared minus 1. So in this situation, my function is invertible, or my function has inverse. Why? Because for each x in here, I have only one value y, right? Which is corresponding to x. And if I pick any y on this interval, which is, on -1 infinity, that means only on this. You see? For each y right here, I have only one x. So I know how to go back to the x. Does that make sense? So in that situation, I'm good. And my function is invertible. All right? So you see, even you consider just one formula, right? But it really depends on how you define the domain, okay? And how you define, the range. Does that make sense? So you may make your function invertible. So based on this example, you can see that, actually the function has inverse if for each x in the domain there is only one y, and for each y in the range there is only one x that is corresponding to the y. So such map is called one-to-one. Okay, just one-to-one. And now I think we can talk about the condition for a function to be invertible. Okay, we can say a function f has inverse if and only if f is one-to-one. Okay, I repeat again, right? One-to-one means for each x in the domain there is only one y in the range, and for each y in the range there is only one x in the domain such that y equal to f of x. Okay, don't forget that. So we have the example right here. Okay, so if we summarize everything in this from what we just discussed, so we need to write out all steps how to find an inverse of a function. Okay, so let's say if you have function y equal to f of x, you need to solve the equation for the x. So you need to find x as the inverse of y, right? Okay, then the last step is you just replace the y in here. You just, let's say, interchange, right, x and y. So you have y equal to the inverse of x. So that is how we can find the inverse. And of course, if you need to verify the condition f composite with f to negative 1x equal to x, and f composite with the f negative 1 right here, f negative 1 composite with the f is also equal to x. So after all these steps, you are good. Make sense? All right, let's consider one more example before we finish this video. Let's find the inverse of the following function. Y equal to square root of 2x minus 3. Okay, and you can see that the domain of this function is Rx such that 2x minus 3 greater than or equal to 0, or x greater than or equal to 3 over 2. Okay, I skip steps in here, so I hope you can see how to solve this inequality to get this domain. And the range of this function should be all numbers greater than or equal to 0, means the interval 0 infinity, because you have square root in here, right? So which is always non-negative. So strictly, we need to say yes, we want to consider the function f from where to where? From 3 over 2, 0. No, 3 over 2 infinity to 0 infinity. You see, we need to stay this, right? Because, as we have seen in the previous example, if we don't stay the domain and the range, the function may not have the inverse. Okay, so now we are good. We need to find the inverse, so we need to solve, this equation with respect to the x. So I square both sides. I get y squared equal to 2x minus 3. Now from here, I will get 2x equal to y squared plus 3. And x is equal to y squared plus 3 over 2. Okay, so from here, I write the inverse function is equal to x squared plus 3 over 2. All right, you have two functions in here, the first one in here and then the second one, the original one like this. So you want to check if they are inverse of each other. So you need to check the identity. Let's say f, compose it with f to negative 1 at x equal to x or not. So let's do this. We have f of f to negative 1 in here equal to, my function is square root of 2. So instead of x in this, right, I need to plot f inverse. Is it correct? So I have 2 right here. The inverse is x squared plus 3 over 2. And then minus 3, right? So if you compare this function with this, right? I simplified 2 right here. And I will get square root of x squared plus 3 minus 3, which is x squared square root. Okay, again, right, if we don't know the position, and of course in this case, right, we need to consider all x in the domain of the inverse. Okay, then what is that? What is the domain of the inverse? It should be also greater than 0, right? Because we know the domain of the inverse should be the range of the original function, you see. So since x is bigger than 0, you get this is just equal to x. You know, don't forget that. Otherwise, square root of x squared should be equal to absolute of x. Don't forget this. But in this case, x is bigger than 0, so you have square root of x squared is just x. We just verified this identity. Okay, you know, this is a long way, but you know, sometimes we have to do all these steps. All right, so I hope that this video is clear enough. In the next video, we will study derivative of inverse functions, and we might consider some other examples. Okay, thank you and see you in the next video.